Welcome class to Chapter 3, Coordinate Systems. This is probably the most important, yet one of the hardest chapters to understand. I don't want to necessarily scare you, but coordinate systems is extremely important when we deal with GIS data and any kind of mapping data. But it's also sometimes poorly understood because there's some mathematics behind it. But we'll try to break it down. I want to give you the theory about using coordinate systems and projections and geographic coordinate systems, and then we'll see how they play out in ArcGIS. So you might be wondering, since we've already done a couple of labs, why all of your data fit on top of each other? Why do they align? And is it always like that? Or is it just something magical that happens in ArcGIS where everything seems to be placed at the exact locations where they should be? Well, the reason why data align is because of its underlying coordinate system. It's like elementary trigonometry or algebra, where you have to map, not really map, but plot x and y. We're going to be dealing with coordinates in the x and the y, and also geographic coordinate systems, which are actually 3 dimensions. So in order to understand your spatial reference, now I want to highlight the term spatial reference. That sometimes is a better way of talking about coordinate systems because it includes 3 major pieces. It includes a datum, which we're going to talk about in a second, the geographic coordinate system, and then the projected coordinate system. Now, if you have a projected coordinate system, that means you must have a datum and a geographic coordinate system in addition. But if you just have a geographic coordinate system, you don't necessarily have a projected system, but you always have a datum. And then we're going to look into tools behind some of these coordinate systems in ArcGIS. Okay, what is a datum? So a datum, I have it basically defined right here. It's essentially a model of the Earth because the Earth is not a perfect sphere. It's actually flattened around the equator. And also, you know, the surface of the Earth is not, it's pretty irregular. So it's a reference surface that we use to sort of, it's like we're pinning down the exact locations of certain features of the Earth so that we can plot our data, you know, and all that data will be aligned with these reference surfaces. So a datum includes an ellipsoid and then some kind of adjustment, and we'll talk about that in a second. Remember, we might think of the Earth as a perfect sphere, but actually the Earth is an ellipsoid, or sometimes it's considered a spheroid, where we actually have a longer distance from one side of the equator to the other compared to the South Pole to the North Pole. And an ellipsoid is a better representation, it's not perfect, but it's a better representation of the Earth's surface. Now, there are a lot of different ellipsoids out there that we can use in our datums. The ones that we mostly use would be Clark 1866, and that's the older version. Back in 1984, the World Geodetic System came into play by using Global Positioning Systems, GPS, and it has a better idea of the size and shape of the Earth, which is the building blocks of our coordinate systems. And currently, as I mentioned down here, we have satellite data that helps us keep a good eye on the Earth and any subtle changes in the Earth's size, shape, and topography. So this is pretty exaggerated, but a geoid is another way that we use different representations of the size and shape of the Earth. A geoid uses geopotential, or we'll just call it gravity potential, and it's a way to try to include the various topography into the size and shape of the Earth. When you're dealing with field data, and if you take GIS 37, you will be dealing with field data as GPS, global positioning systems, and you really need to know what your geoid is. So this figure over here, I like to think of this as a building block. Okay, so we know the Earth is a sphere. That's the most basic way we represent the Earth, unless it's a map, but we're dealing with 3 dimensions right now. An ellipsoid attempts to represent the flattening of the Earth around the equator. A geoid, again, attempts to include topography in there, and then you have your actual topography. So you realize right now that a sphere, an ellipsoid, and a geoid are all representations of the Earth, but they're not very good. I mean, they can be good for certain uses, but when it comes to coordinate systems, we need something else, and that something else is a datum. So once again, we have a sphere, then we have a spheroid, which is flattened, and then we have a geoid, which attempts to include topography in the flattening of the Earth, and then we try to fit an ellipse around the geoid. Fitting the ellipse around the geoid is considered a datum. And as you can see, some places it's a pretty good fit, but other places, like right here, a bad fit. So not all datums work well around the world. In fact, most datums only work in a very local region. So once again, these are all attempts to approximate that flattening shape of our Earth. And not all datums work in all places. In fact, most datums are only used locally. So a horizontal datum, which is what we basically will be focusing on, is just, it's like a collection of bench points that helps us identify where exact latitude and longitude coordinates are. A geographic coordinate system uses latitude and longitude, which hopefully you have heard of or you have studied in a previous geography class. We also have vertical datums. I'm not going to talk too much about that in this chapter, but a vertical datum that is often used in GIS, at least in North America, is the 1988 version. It's the most accurate, and it's based on, again, GPS data. Okay, so what kind of datums are used for North America? We used to use the North America datum 1927, which was based off of the 1866 spheroid, which is also an ellipsoid. But back in 1983, we began to use the North American datum 1983, which is based on an updated GRS 80, which represents 1980 when it was basically calculated, and it uses GPS data. Now, most GPS devices use the World Geodetic Survey, WGS 1984, and that is actually a worldwide datum. It's really, again, used for GPS units around the world. Fortunately, the WGS 1984 and the NAD, North American Datum 1983, are almost identical within North America. So often, when we gather GPS data, we can go ahead and use it in ArcGIS because it matches pretty closely to the North American datum. So I've just highlighted here, again, the 2 main datums that we will be using in North America, because much of our, I think almost all of our mapping will be within North America. So eventually we are going to talk about projections, but what I want to just mention to you right now is that every data set has a baseline geographic coordinate system, and they use latitude and longitude. If it's projected, then it uses a projected coordinate system, and it's a flattened version of, it's like a map version of the globe, and we use XY coordinates. Regardless, both of these will have a baseline datum. And this figure right here, we are looking at the difference between NAD 83 and NAD 27. The photo is in NAD 27, but the rows are in NAD 83. So you could have an offset of up to 300 meters, depending on where you are in North America, if you use different datums. Now you have the option in ArcGIS to change datums. You have to have a formula or calculation that's already in ArcGIS to change that. But nonetheless, it's really a good practice to have most of your data in the same datum and even in the same geographic coordinate system and projection. So these are location differences between NAD 27 and NAD 83. The area where we see very little difference is in eastern Illinois and in west central Indiana. Over here in Southern California, we have offsets up to 80 meters. Now, zooming out, that might not be a big deal, but if you're zooming in using a very large scale, that could really make matters really pretty worse when it comes to plotting data. Okay, so that was some information on datum, and I want to mention this to you now, and I should have mentioned this to you earlier. This video might be something you're going to want to watch a couple of times, and you definitely want to read the textbook. There's a lot of technical details with this, and it takes a little bit of time. That's why we're going to have 2 labs covering this one chapter. Alright, so let's talk about geographic coordinate systems. You have probably used Google Earth in the past, and it looks a little bit like this, where you have your longitude values here and your latitude values over here. And they are spherical coordinates. Latitude and longitude values are actually angles, and they represent basically degrees around a circle. Okay, so with latitude and longitude, let's start with latitude. Latitude measures distances north or south of the equator. Their lines run east and west, but they measure distances north and south, up to 90 degrees north at the North Pole and 90 degrees south at the South Pole. With lines of longitude, they run north and south, but they measure distances either west of the prime meridian or east of the prime meridian, and we can have a value up to 180. So together with latitude and longitude, we can plot precise locations on the 3-dimensional version of the Earth. So once again, these are spherical coordinates. So let's just take a look at 60 degrees north. Technically, even though we know that this dot right here is 60 degrees north, there's a line that goes through the center of the Earth and the point that's 60 degrees north, and another line that goes from the center of the Earth to the equator. That angle between there is 60 degrees. So once again, latitude and longitude are angular distances. So there's some formats that we deal with when it comes to latitude and longitude. We can do degrees, minutes, and seconds, or we can just do decimal degrees. Decimal degrees are pretty easy to understand. You basically have your latitude and your longitude with a decimal. Degrees, minutes, and seconds. So 1 degree is 60 minutes and 1 minute is 60 seconds. Now, depending on where you're located, the space between degrees of longitude can change, where the space between latitudes values really don't change too much. Just for your information, Pierce College is at 34 degrees, 11 minutes, 6 seconds north, 118, 34 minutes, 43 seconds west. Another way of doing this is using positive and negative values. Positive values represent north for latitude and east for longitude. So together, once again, we can have latitude and longitude. This is just another representation of that. Down below I have it in degrees, minutes, and seconds. Using, instead of north, south, east, west, I'm using positive and negative values. That's the basic underpinning behind a geographic coordinate system. with projections. So hopefully, again, you have seen projections in the past in a different geography class, and if not, we'll go over a little bit of the details here. Map projection. Now keep in mind that maps are representations of Earth, and Earth is a sphere, or as we just learned, is really an ellipsoid. So when you represent something that's 3 dimensions using a 2-dimensional object, you're going to have distortions. Every projection causes distortions, and the level of distortion can be minimized or move around or applied to a map property compared to another map property. And that's what is so powerful about GIS, is it can do all of that very quickly. Where back in the day when we had to create paper maps, using a specific projection sometimes was very difficult. So as an example, let's say here we have Earth and we have a globe. And a globe is the representation of an Earth. It's like a model. Let's say we peeled back this globe like we're peeling an orange. You would have this as a result. Now I bet you've never seen a map that looks like this. What happens is extra spaces, extra land and water is added to this, especially near the North and South Pole, to make the map basically look better, but it also is not as accurate. In fact, one of the most inaccurate pieces of world maps is Greenland. I believe Greenland is technically 17 times smaller than Africa, but on a map projection like this, the polar regions are greatly distorted. So one way you could think of a projection is like putting a light bulb into a transparent globe, and then you're wrapping a sheet of paper around that globe. You're drawing, let's just say, outline of the continents onto that piece of paper, and then you roll that piece of paper out. That basically is where the term projection comes from. But in GIS, it's really a mathematical process of transforming something that's 3 dimensions into 2 dimensions. And again, different datums may give you different results on this, because a datum helps you understand the size and shape of the Earth. So all maps have distortion, but the type and degree will vary. Some have distortion of area, or actually, let's do it like this. Some preserve area. Some preserve, well, actually, if you think about this, this label is telling me what is actually distorted. So look at Alaska, look at Greenland. Those are greatly distorted by area. But look at this over here on the right. Shape is greatly distorted here, but the size of features are about the same. Whereas on this side, where it says area, the shape is preserved. Where area is preserved, distance is preserved. And where shape is preserved, direction is usually preserved. And this really makes a big difference when you're dealing with world maps. If you're zooming in to smaller areas, luckily the distortions are not as noticeable. And if you really zoom in, you may not notice the distortion at all. But technically, we're still representing something that's 3 dimensions onto a 2-dimension object. Okay, so we can lump these projections into basically what property is being preserved. So conformal projections represent true shape and angular relationships, but look at the size of things. Look at Antarctica. That's definitely not what Antarctica looks like. It does look like that. I mean, the border of Antarctica looks pretty good, but the size is greatly not just distorted, but it's just a false representation. And then Greenland, of course, is much bigger than it actually is on Earth, or even on a globe. Now, we could go the other way. We can keep area preserved, but then the shape is distorted. I mean, Greenland does not look like this. However, now the size of Greenland is better represented compared to, let's say, Africa. Once again, we often have to decide what is the most important property to preserve. So this type of projection is called an equivalent projection. So I like to think of it really as there are 4 types of projections. You have your cylindrical projection, which is like the Mercator projection that preserves shape but not size. Conic projections we didn't talk about yet, but this preserves the mid-latitudes really well. Cylindrical ones are good around the equator, conic ones are good around the mid-latitudes, and then you have azimuthal projection types, which are good at the poles because it just touches at one spot. And then the 4th type is basically a mathematical type that tries to redistribute various types of distortion throughout the world so that not one place has a greater distortion than the other. In addition, when we're dealing with cylindrical projections, we often have either a tangent projection, where this imaginary piece of paper touches the Earth at one latitude or one longitude, or we have secant projections. These secant projections touch the globe at 2 latitudes or 2 longitudes, and the area that's actually touching the piece of paper, there's no distortion. So if you can have 2 lines that have no distortion, that makes your map even better. So some more specific names. If we have a cylindrical projection and that cylinder is just like a coffee can or a soda can standing straight up, we can have Mercator, which is the one we talked about earlier, which is not really good, or we can have transverse Mercator, which is a lot more common. Transverse Mercators are more localized. And then if we have a transverse cylindrical, we could have cylindrical equal area and equirectangular. Again, these are all just theoretical concepts behind projections. We'll talk much more in detail about more specific projections in ArcGIS. Cylindrical projections are pretty useful if you want to draw what's called a great circle route. A great circle route is the route an airplane would fly across the world. What's interesting is most people don't think of the world as 3 dimensions, they think of it as a 2-dimensional map. So if you're going from San Francisco to London, you might think that your airplane would run along what's called the rhumb line. Actually, your airplane would go pretty far north. It would probably go into northern Canada and Greenland back to London. It's actually the quickest way to get from one city to another. Conic projections, again, these are just general types. We will deal with Lambert conformal conic. Remember, conic projections are good for the mid-latitudes. Sometimes you might have an equidistant conic. Albert is equal area or polyconic. Polyconics we're probably not going to use too much in this class, but Albert is equal area and Lambert conformal conic. Conformal means that the shape is preserved. Equal area means that the area is preserved. These are just some general maps that we don't use in ArcGIS, but they represent the 2 types of conic projections. And then azimuthal. As you already know, the polar regions are greatly distorted by a lot of different projections. But if we put an imaginary piece of paper at a point, in fact it could go anywhere, but most of these azimuthal projections are at the poles. So we have various, you might actually be dealing with in your homework, we have various projections for certain areas in the polar regions or in and around Antarctic. The only one that isn't polar is this azimuthal equidistant, but Antarctica often has its own set of projections, and so does the Arctic. Again, these are some examples of azimuthal projections where right at the north or south pole you would have no distortion, and then the distortion would increase as you go away from the poles. You could see, some differences between, let's say, the Mercator projection and the equidistant conic. These are again some, complex concepts, so let's talk about this again. Mercator, remember, it distorts distance and area, but it preserves direction and shape. This is the shape of Greenland, but it's not the size. Whereas in equidistant conic, distant is the key term. That means it preserves distant and an area to a certain extent, but it distorts direction and shape. Now remember that fourth category. One of those projections that tries to distort just a little bit all four major properties. Again, the four major properties are size, shape, area, and distance. So it uses mathematical equations to distribute the distortion evenly across. So some places might look better than others, but in general it's a good way to map the world. Again, it's not perfect because look at Antarctica. Antarctica, it looks better, but it's still not what it looks like. Now, when we get into specific projections, you're going to see differences between certain kinds of projections. However, ArcGIS has this feature where it will project your data on the fly. As long as your data set has a correct projection, it'll project it and match it to whatever projection is being used. So you may not always see these subtle differences in projections. But one of the things that we will look at is how the United States, what is the best way to represent the United States? Most of the time, you might see the United States being represented like a Mercator, where the boundary between the US and Canada is a straight line. But in reality, what we should be using is a Lambert conformal conic, where the boundary is a curve, because again, we're dealing with a three-dimensional object. Okay, so how do we deal with geographic coordinate systems in ArcGIS? So geographic coordinate systems in general are not a good thing to use. You might want to use it if you're giving data away, because that way a person can go ahead and just project whatever they want, whatever projection they want to use. But in general, for mapping and analysis, geographic coordinate systems are just not something you want to use. Projected coordinate systems, now those are what we want to use, and these have this gives you a better capacity for mapping and for analysis. So projections, we're taking something three-dimensional and we're creating a two-dimensional representation of that, and we use X and Y. The most common type of projections are UTM, Universal Transverse Mercator, and the State Plane Coordinate System. We'll talk about those in detail. Keep in mind, you might be thinking, well, geographic coordinate systems, they actually represent the Earth because they're in three dimensions, so how could a two-dimensional object be better than a three-dimensional object? Well, technically, because you're looking at a screen, everything is two dimensions. So you might as well go ahead and project that three dimensions into two dimensions. And we're looking at smaller areas, so the distortion that occurs is actually pretty minimal, because these various UTM and state plane coordinate systems are covering a very small area on Earth. So let's talk Universal Transverse Mercator, UTM. Over here, you could see that basically a UTM coordinate system represents a very thin slice of the Earth. And that way, distortion is pretty minimal within these zones. So these zones run north to south. California actually has zone 10 and 11. You will also be dealing with Austin data, so that uses UTM coordinate system zone 14. There are 60 zones. Each zone is 6 degrees wide, and this is really a good way to map something that has a north-south orientation. So remember, a projection is always based on a geographic coordinate system, which is always based on a datum. So eventually we will learn how to read this. This projection right here is NAD 83, that's the geographic coordinate system. Well, technically NAD is the datum, and then UTM zone 60 north is the projection. And we'll talk about some of these other terms later. Here's just one map showing all 60 zones. Really, we're just going to be focusing on North America though. Okay, this is a closer view of these UTM projection zones. As you see, each projection zone, or just, we can use zone, has a central meridian. And we'll talk in a minute what we mean by that in terms of false eastings and false northings. Okay, so let's deal with Mount Rushmore. Mount Rushmore is in 13 north, that's the zone. And what we're going to do is look at what a false easting and false northing might do. Because we're in the Western Hemisphere, our values are technically negative. So in order to get this, technically it's an X value of 623,733 meters, we have to add 500,000 meters. That's our false easting. Now, because Mount Rushmore is in the Northern Hemisphere, and that's positive, we do not need a false northing. It just automatically is 4,859,580 meters north of the equator. However, if you're dealing with the Southern Hemisphere, then we have to use a false northing, and that false northing value is 10 million. So because Sydney, Australia is 3,747,732 meters south of the equator, if we add 10 million, then we have 6,252,268 meters, which again is positive. So we use false northings if we're mapping in the Southern Hemisphere, and we use false eastings if we're mapping in the Western Hemisphere. As another example, we have Montgomery, Alabama. It is 566,000 meters east because of our false easting of 500,000 meters. But it has just all by itself a positive north coordinate, 3,581,300 meters. And this is in zone 16. Now that is UTM. Now state plane, what state plane does is it actually breaks up different states into various zones so that you have even less distortion when you're mapping it out. So you just have to, and we'll look at a map at exactly what those areas are. Essentially, in certain states, if the zone has a more north-south orientation, it uses a transverse Mercator. But if it has a more east-west orientation, it uses a Lambert conformal conic. Sometimes state plane zones use feet, so you got to be careful. The UTM uses meters, and a lot of the state plane ones, especially with NAD 1983, will use meters, but sometimes you will see feet. Now we haven't really talked about this, but this is what it looks like in ArcGIS, and this is something that I'll probably show you even more in class. Essentially, when you're looking up the projection information, this is what you would see. And so pretend that we're looking at Hawaii, and we have a NAD 83 state plane, Hawaii Zone 3. its primary projection is transverse Mercator. It has a false easting of 500,000 but no false northing. Its central meridian, that talks about the zone itself, the scale factor, which we probably won't get into too much, and then the latitude of origin, which is another very important piece when it comes to projections. Basically, you have a central meridian and a latitude of origin that sort of anchors down this projection using latitude and longitude. So this is a map showing you the various state plane projections. California has 6 different zones, whereas Montana just has 1. So it's pretty arbitrary in terms of what or how many zones each state has. Now, if we're using either state plane or UTM, once again, we have to understand the coordinates. So I want you to just keep in mind, look at this coordinate here. We have 2,478,424.96 east, and really for north it's only 531,000. So that's a little different from UTM. State plane zones can have different coordinates and different false eastings and different false northings, if we even have a false northing. And the information about that will be within the data set that you can look at in ArcGIS, and we'll talk more about that in class. Topo maps are actually very useful in terms of projections, because sometimes topographic maps, which basically show you contour lines of various areas, will have a geographic coordinate system in latitude and longitude, and if you're lucky you might have both state plane and UTM. So you have these state plane and UTM values that are especially useful if you are trying to georeference one of these in ArcGIS. Okay, so we talked a lot about the theory behind these spatial references, behind datums, ellipsoids, geoids, geographic coordinate systems, projections. Now, let's breeze through a little bit about the tools. Again, I want to show you tools much more in detail in class. So remember I told you where you're going to get that information from? Just like you would if you had to relink a data set, you would open up the properties of your layer in the table of contents, you go to source, and you can get all of this information if you are projected. And you know you're projected if you have very large coordinate systems, or I should say very large coordinates. However, if you open up something that's only in a geographic coordinate system, like WGS 1984, then your coordinates are just going to be in latitude and longitude values. This is important because unfortunately you may get data from whatever source, whether it's online or from a different company, and you may not know, and they may not have defined that projection. They may not have given you what the projection is, and it's completely blank. Well, the first thing you would look at is, are my values for my extent really small, from 90 to -90 or so, or are they very large? If they're small, then at least you narrow down that you have a geographic coordinate system only, which basically means it's unprojected. But if it's projected, then you have most likely very large values because they're in meters and not in decimal degrees. Within our toolbox, there are two primary tools that have to do with projections, and this is extremely important. People, especially in the beginning, often confuse these two tools. Define projection is used only when you have to label a projection. Let's say, again, you have this data set, and let's say you have the data set, but they didn't define it for you, but you have in the metadata that it's WGS 1984. You would then open up our toolbox and use define projection. You only use project if you want to turn something that is already projected correctly, and you want to basically transform that into a different projection. Do not use project when you want to label, or do not use define projection when you want to change the projection. That is the most common cause, and I'm going to highlight it here, the most common cause of coordinate system problems is confusing the project and define project tools. And we'll talk more about this in class. And you could also set a predefined coordinate system when you open up the properties of a feature class. I usually don't do something like that, but you got to be very careful in this case too. So we'll go over this lecture again. You might want to watch key features, read the textbook, because this is extremely important stuff, and it'll take you a little bit of time to get a good handle on this. So don't get discouraged. Let me know if you have any questions, and I'll see you in class. Thank you.